සමහරු කියනවා කවර කළා කියලා සමහරු කියනවා කවර කළේ නැහැ කියලා. ඒ මොකද ඒ? මම හිතන්නේ ඔයගොල්ලන්ට ෆස්ට් ඉයර් එකේදී සිලෙක්ෂන් එකක් නැහැ නේද? මම හිතන්නේ තියෙන ඔක්කොම කෝසස් කරන්න ඕනනේ. Still doing. Okay. Right. Okay. Then we'll start working on this topic, right? Right. As usual, I will start with a story. You like stories, right? Katandara වලට ආසයිනේ. Now, this is a story, not actually a story, a scenario. Right? Let's say you decided to change your residence. Now you are at a new place, maybe a new town or a new village. Okay. I don't know anyone in this village. So you want to know where to find the your everyday needs, like rice, sugar, dal. You need to buy these things, right? To buy these things in this little village, there are 4 shops. And price in these shops are roughly the same. Right? Maybe they have standardized the price, right? The government says, okay, you have to sell this at this particular maximum retail price, right? Maybe because of that, prices are almost the same. So price-wise, you have no issue with any of these shops. They still look the same. But you are a little bit concerned about people who are cheating when they are selling. For example, sometimes they adjust the scale, so the amount or the weight that you are seeing is not the correct weight, right? I don't know. You may have heard of these things, right? Sometimes the sellers and vendors get arrested because they are using incorrectly calibrated scales and weights, right? So like that. So you are not sure whether these shop owners are honest or not. From your past experience, you know that maybe some of them are cheating when measuring the weights. Right? You ask for 1 kilo rice and they give you only 950. Right? So you want to get an idea whether these shops are honest, or let's say measure the weights accurately. Not the word accurately, let's say correctly. There's a small difference between them, right? So now you are an undergraduate in the university, so you decide to do a scientific experiment to see whether they are cheating or not. So how do you do an experiment? Now this is a stat type of thing, right? Now you already know a little bit about stat. So you decide to take a sample. Last day we talked about samples, right? You decide to take few samples from each shop and see what it looks like, whether you can see whether there are any cheatings or whether they are honest. So this is how you do the experiment, right? You go to each shop and from each shop you buy, let's say 1 kilo of rice, right? That's the idea. But then later you decided, okay, having one sample may not be good. Let's have 5 samples from each shop, right? So you go to shop 1 and ask for 1 kilogram of rice and maybe another kilogram of dal, another kilogram of sugar, like that, 5 different items. Even if it is the same item, that's okay. But 1 kilogram. So you have a sample of 5 items from each shop. And each of them are supposed to measure or weight 1 kilogram. Right? The reason you want multiple samples is just one might not be good. Maybe there's a random chance that something has happened. So from a one sample, you can't tell much. But if you have multiple samples, then you can get a better idea. So that's why you are getting 5 samples from each shop. And then you go home. Let's say at home, you have a very good scale, right? This one is so good, you can measure it up to, let's say, 1 milligram accurately. It's properly calibrated, everything is set. So you can measure it. So now you have 4 shops. Let's label them as shop A, B, C, and D. So in the shop A, you measure the first sample. Let's say it's around 900 grams. It's not that good. You ask for 1 kilogram, the shop owner had given you 900 grams. Then you measure the second sample from the same shop. It's again like 910. Third sample is like 890. So like that. So when you measure it, you realize all the samples are very close to each other. The weights are very close to each other, but they are different from 1 kilogram. All of the samples are very close to 900. That's shop A. And then you go to shop B. Samples taken from shop B. I'm not sure why someone is putting a phone number there in the chat. Anyway, so in the shop B, again, you have 5 samples. You measure the actual weight. This time, weights are very close to 1 kilogram. Let's say 1005, 1010, 990, like that. So 5 samples are very close to each other in weight, and they are very close to the correct value as well. So that seems to be a good idea. Shop B is like that. Then you go to shop C. Samples taken from the shop C. Now this might be old shop. So he is using the old type scale. Not a digital one, right? So when you look at his items, you realize the values are all over the place. Some samples are 1,100. Some samples are 900. Some samples are 980. Others are 1,050. So they are all over the place. Some are very high, some are very low. That's shop C. The last shop, you measure it and you realize the distribution is not that spread. So values are close to, let's say something like this. Values are spread around 1 kilogram. So some samples are like 1,050, others are like 1,980, like that, right? So you have these 4 different shops with 4 different scenarios. Sometimes you get values very close to each other. Sometimes the values are, or the values you get in the samples are far away, distributed in a wide range. Sometimes you have values close to the correct value. Sometimes you have values far away from the correct value, right? So altogether you have 4 these possible combinations. So now let's put some names into this scenario. Before going to the next slide, I want to make sure everyone understood the example I mentioned. මම කිව්ව උදාහරණේ තේරුණාද? අර කඩ හතරක් ගැන කිව්වේ. කඩ හතරෙන් අපි සාම්පල් පහක් ගත්තා, කිලෝ එක ගානේ මැනලා. හැබැයි ඒවයි තිබුණේ එක එක විදිහ. සමහර කඩවල හරියටම තිබ්බා, සමහර කඩවල හැමතැනම එක එක සාම්පල් එක එක ගණන්. තේරුණා අය ඉන්නවා නම් අත උස්සන්න. ආයි කියා දෙන්න ඕනේද? Is it okay? Yes? No? Did you get the idea? Good. Very good, very good. Right. Now we will go to the next slide. Now what I mentioned is a everyday scenario Now, stat and physics and science, all of them are very related to everyday scenarios. Only thing is, sometimes we don't get the examples from everyday. Sometimes we have new terms for them in our science and math. But if you look carefully, most of them are common sense concepts, right? So here's the statistical term. This is, let's say, each of these dots represent a weight in your sample. Here, I think we have about, I don't know, 10 different samples, not 5. So at the center is the correct weight. Now, this is not actually a graph. If you are putting a weight, you can't have a 2D kind of this kind of image, but this graph, or sorry, not a graph, this image is to help you understand two different terms. One is called the precision, one is called the accuracy. This is like a dartboard. You want to hit the middle. That's the idea. Now, if you look here, this is like the shop 1. You can see all the samples are very close to each other, like 900, 895, 905. So values are very close to each other. However, they are not correct values. They are far away from the correct value. So this kind of scenario we called as high precision and low accuracy. Precision means how close the values are to each other. If you repeat something, can you get same or approximately close value? If you do something 10 times and you get values very close to each other, that has a high precision, high repeatability. Accuracy means how close it is to the correct value. Here we want 1 kilogram, 1000 grams. This might be 900 grams, so it's a little far away. So this section says you have high precision but low accuracy. This is like the shop B. Now in the shop B, you have very high precision. That means all the measurements are very close to 1000 grams, very close to each other. And it has high as well. High accuracy means they are close to the correct value as well. They are close to the correct value as well. This is the another case, third case. Here, you can see values are averaged or spread around the correct value. So if this is the 1000, some values are a little bit higher than 1000, some values are less than 1000, but overall they are around the value 1000. Here the values were a little bit away from 1000. Here values are around 1000. However, they are not close to each other. So if you ask for 1 kilogram, you might get 1100 grams, or you might get 900 grams. We don't know. But if you take about 10 or 20 samples, average will be around 1000. So that's the idea. So this is called low precision, high accuracy. Low precision means the each value is spread far away. High accuracy means, but it is spread around the correct value. Spread around the correct value. This is the last case. Here, spread is far away and the values are also spread around a wrong value. So this is called low precision, low accuracy. Low precision, low accuracy. So let's label them as some numbers. Just for the sake, I'm going to say P, Q, R, and S. So if you are going to let's say you want to now, your experiment is complete. You want to go ahead and buy some items from a which shop do you think is the most honest shop? PQROS. Q. Okay, good. Which shop do you think is cheating? Which shop do you think is cheating? P. Okay. Which shop do you think need to upgrade its scale or weight measuring mechanism? There can be more than multiple answers. Which shop do you think should update their weight updating mechanism? All right. For the last question, actually, you have two answers, R and S. Why? In both of these cases, weights are all over the place. So you want to measure 1 kilogram, but you end up actually putting 1,100 or maybe 900. So both these scenarios are possible. Only thing is, in case of R, maybe that person is trying to cheat, or maybe that there's another error in the scale. Maybe it has some kind of, maybe it has worn out or some kind of error. A little bit later, we'll talk about something called systematic error. So that possibility is also there, right? Right. Now you have an idea about precision and accuracy, right? So I have not used, so you may have not used these exact words in your everyday life, but from your answers, I know you have the gut feeling. You have an idea in your head what these words mean. So now you have to memorize or match your that feeling into these two words, right? Because in the exam, you can ask for precision, accuracy, and all these things. So when you say precision, you should have the idea what is precision and what is accuracy, right? Because these are two different things. Now in loose context, sometimes we use it as equal terms or synonyms, but they are not. If you are to be very precise, these are two different terms with two different meanings. Right. I hope now you understood the difference between them. Just here's a more formal kind of definition for this one. Accuracy is how close each of these. Now, if you look at this one, you can see it is far away from the correct value. So accuracy is how close your values are to the correct value or the true or the accepted value. Precision means how close your measurements are to each other. Are they agree upon each other? If you repeat something, will you get the same answer? Now, uncertainty is the combination of both accuracy and the precision of the measurement. So uncertainty is the combination of both. So when you are taking a measurement, you talk about uncertainty. Right? So there are types of errors. We have random errors and we have systematic errors. Random errors means the error can be anywhere. It can be a positive error or a negative error. It can have different values. Systematic errors means it's almost the same. Whatever the error, it's roughly the same value. Same kind of error is happening every time. Right? So let's look at some of the examples. Okay, here we don't have that slide. So let's talk about this random error and systematic errors. Let's say you are trying to measure a length using a meter ruler, but let's say not you, your friend. Okay, otherwise you will get offended. He's trying to measure a certain length, but he doesn't have a good eyesight, right? So he used to wear spectacles, but unfortunately this day he had forgotten the spectacles. So everything seems to be a blur. when he's measuring, sometimes he put the mark before the actual value, sometimes even after the actual value, because it's a blur. He is not sure where to put the dot. So that kind of error is a random error, because it can be larger or smaller than the actual value. It's random. Or let's say a different scenario. You have this meter ruler, but unfortunately it's a low quality meter ruler, right? So these rulers are made from different materials. Let's say it's made from wood, and due to humidity, it has expanded a little bit. It can happen, right? Made from wood, but it has expanded with this rainy weather. So now every time you are measuring a 1 meter, you will be measuring a little bit larger than 1 meter. It will always be larger. That type of error is known as a systematic error. That is known as a systematic error. The error has a particular pattern into it. Not random, it has a particular pattern. So the example I gave is a very simple one. So it will always have maybe, let's say, 3 millimeters larger than the actual value. So that's a systematic error. Sometimes systematic errors can be a little bit more complicated. Maybe you have a sensor to measure the temperature. For the low values, its reading is, let's say, 0.1 Celsius above, the correct one. But for high values, as the temperature goes up, this deviation also increases. For 10 Celsius, you have a systematic error of 0.1. But for 20 Celsius, you have an error of 0.2. And for 30 Celsius, you always get a value always get a value 0.3 Celsius larger than the actual value. So now, again, a systematic error, but it's not a constant. It is called systematic because it has a particular pattern, right? You can predict it. Now, handling of these errors are again done in two different ways. If you have random errors, the best way to detect and to correct random errors is to repeat the measurements. So if you do the experiment 10 times, you can look at the values. Are they close to each other or are they far away spread? If values are far away from each other, that means most likely you have a random error. And removing the random error is a little bit easy. You take the average value. That's one way of removing the random error. Not removing, reducing the random error. Because you believe all this randomness is spread around the correct value. Right? Like in here. Values are far away from each other, but if you average it, you expect it to be close to the correct value. Now, systematic errors are something like this. You always get a particular way of difference. So to detect the systematic error is a little bit hard, because although you repeat it, you always get the same number. So you think it's correct, but actually it's shifted. So only way to find the systematic error is to compare it with a different instrument or a different experiment result. But once you find the systematic error, correction is very easy, because you can find a formula for the correct value and the measured value. You can apply and get the actual value or the correct value. Right. So those are the two different types of errors: random errors and systematic errors. Is it clear these two types of errors and how to correct them? Yes, no, maybe. Line එක හැදෙන්නේ නැහැ පුතේ. කොයිකද systematic එකද?
ඔව් සර්.
ඒක පැහැදිලි කරන්න ඕනේ.
ඔව් සර් චුට්ටක් පැහැදිලි කරන්න ඕන.
හරි. මම සිංහලෙන් පැහැදිලි කරන්නම්. හැබැයි කාට හරි ඉංග්‍රීසියෙන් පැහැදිලි කරන්න ඕන නම් කියන්න මම මේක ඉංග්‍රීසියෙන් පැහැදිලි කරන්නම්. හිතන්නකෝ අපි දැන් අර කඩේ සිද්ධිය. දැන් පළවෙනි කඩේ ගත්තොත් අපි කිලෝ එකක් ඉල්ලුවම හැමතිස්සෙම හම්බ වෙන 900ට කිට්ටු ගාණක්. බැලුවා මොකද කරලා තියෙන්නේ පඩියක් යටින් තව කැල්ලක් එල්ලලා. එහෙම කරනවනේ සමහර හොර වැඩ කරන්නේ. තරහාදී බඩු දාන පැත්තට පොඩි කැල්ලක් යටින් එල්ලලා. එතකොට මොකද වෙන්නේ? හැමතිස් අපිට මේ එල්ලපු කැල්ලේ බර ග්‍රෑම් 100යි කියලා. හැමතිස්සෙම අපිට හම්බ වෙන්නේ ගානට වඩා ග්‍රෑම් 100ක් අඩු වෙයි. කිලෝවක් එල්ලුවොත් හම්බ වෙන්නේ 900යි. 500ක් එල්ලුවොත් හම්බ වෙන්නේ 400යි. කිලෝ දෙකක් එල්ලුවොත් හම්බ වෙන්නේ 1900යි. එතකොට එතන පැටර්න් එකක් තියෙන එක සිස්ටම් එකක් තියෙනවා. හැමතිස්සෙම මනින ගාන ඇත්ත ගානට වඩා ග්‍රෑම් 100ක් අඩුයි. ඒ වගේක් අපි ගන්න සිස්ටමැටික් එරර් එකක් කියලා. රැන්ඩම් එරර් එකක් කියන්නේ ඔක අනිත් පැත්ත. අපි හිතමු දැන් වෙන කඩයක් තරාදිය තියෙනවා. හැබැයි තරාදිය මලකඩ කාලා. හිටපු ගම හිර වෙනවා. සමහර බඩු තියෙන පැත්ත පල්ලෙහාට ගිහලා හිර වෙනවා. සමහර වෙලාවට පඩි තියෙන පැත්ත පල්ලෙහාට ගිහලා හිර වෙනවා. එතකොට මොකද වෙන්නේ? සමහර වෙලාවට ඉල්ලුවට වඩා අඩුවෙන් හම්බ වෙනවා. සමහර වෙලාවට ඉල්ලුවට වඩා වැඩියෙන් හම්බ වෙනවා. එතකොට අපිට හරියටම කියන්න බෑ මේක ග්‍රෑම් 100ක් අඩුයිද ග්‍රෑම් 100ක් වැඩිද නැත්නම් ග්‍රෑම් 50ක්ද මොකද්ද වෙන්නේ කියලා. ඒ වගේ එකක් අපි කියනවා රැන්ඩම් එකක් කියලා. ඒක සිස්ටමැටික් එරර් එකක් ගොඩාක් වෙලාවට ඉන්ස්ට්‍රුමන්ට් එකක තියෙන බිල්ට් ඉන් එරර් එකක්. ඒක හැමතිස්සෙම එකම විදිහට වෙන්නේ. නැත්නම් මීටර් රූලේ උදාහරණයක් මීටර් රූල පෙඟිලා පොඩ්ඩක් දිග වැඩි වෙනවා. එතකොට මනින හැම මෙෂර්මන්ට් එකම වැඩියෙන් තමයි වෙන්නේ. ඒ වගේ මොකක් හරි ක්‍රමයක් තියෙනවා නම් හැමතිස්සෙම එකම පැත්තට එකම විදිහට පැටර්න් එකකට එරර් එකක් එන එක අපි ඒකට කියන සිස්ටමැටික් එරර් එකක් කියලා. පැහැදිලිද?
සර් හරි සර් හරි.
Okay, so let's go to the next slide. Then you have not next slide, you have got 3 or 4 different slides. This is more related to physics. So I told you in the physics and science we do a lot of experiments and we should know about the possible errors. Everyone can make errors, right? Not even in undergraduate, even in large labs. For example, I remember there was one time an error made by the CERN about a particular speed particle, right? So now CERN is considered to be one of the top physics research labs, but they made a mistake, right? So everyone should be aware of errors. What can cause errors, how to correct them, things like that. So there are different ways you might get errors into your reading. First one is called the incomplete definition. Let's say you are asked to do a practical. In the practical, you have let's say you have elastic string. You are asked to measure the length. But the question doesn't say whether you have to stretch it and measure the length or whether you have to measure the while it is in relaxed or thick. And if you have to measure it when it is stretched, how much you have to stretch it, right? So here you are, the definition is not enough. You are asked to make a measurement, but all the things are not well defined. You can take the measurement in different ways, so the values might be different. Maybe you are asked to measure, let's say, a particular amount of grain, let's say paddy. You are asked to measure 50 grams of paddy for a particular experiment. But it doesn't say whether it's dried ones or just came from the field or whether it's, I don't know. With the time, the weight can change, right? because the paddy get dry. The water level content is less. So 50 grams of dry paddy and 50 grams of fresh paddy have two different amounts. So then you have to be clearly say, what do you want to measure and what kind of constraints or other things you have to consider. So if you didn't put that extra description, different people will try to measure it differently. Then you will get errors. So it can be systematic or random depending on how you are going to measure it. Right? Second one, when we are taking, we make certain assumptions, right? Or sometimes we try to take the experiments simple by removing some factors. For example, let's say you want to measure of a project ball and you want to know how long it takes to hit the ground. Equation might have a certain equation like equation of motion, but in that equation you don't have this. So when you are doing that, if you want to validate that equation, you have to do it in a vacuum. But you don't have a vacuum, so you do it in the classroom, but then you will be getting a resistance, right? You will have a drag force. It might be small, but it can still cause a small error. Of course, it depends on the experiment you are doing. If it's just a drop of a ball, it might not be much of an effect. You might neglect it. But let's say you want to design a shape of a vehicle, then air resistance or the drag is very important. Otherwise, your mileage will drop. So like that, sometimes you neglect or fail to account for certain factors. That can also cause errors. You can have environmental factors as well. For example, if you are taking an electronic measurement, you might have a power line going close by and it might induce some noise. Right? Or you might be measuring a weight, a very sensitive measurement, but there might be a ceiling fan on top of it, so that due to that airflow, the value might be different. So environment again can cause errors. And we have the instrument limitations. Now you can't use a meter stick, let's say 1 micrometers. Why? Because the minimum thing is your minimum scale is 1 millimeter. So if you look at the half of this per scale, you have only 0.5 millimeter accuracy. So like that, there can be instrumentation errors as well. You are trying to measure a weight of a very small thing, let's say, I don't know, seed of a pepper seed. But you are trying to measure it using a scale that is designed to, let's say, up to 10 kilograms. Then you will get some errors. So instrument resolution is again important. And we have calibration errors. Calibration is sometimes you have to compare it with a standard value and make sure it is measuring correctly. For example, if you look at oscilloscope, before taking any readings, you have to calibrate it. Oscilloscope have a built-in output to calibrate it, right? So if you have to calibrate or if you didn't calibrate it properly, you get an error. Now, this type of errors are systematic, okay? And sometimes you have zero offset. I think in A levels also, you may have also covered this particular offset, like in micrometer calipers or screw gauges. You make sure you either make sure it's zero or if you have an offset, you measure that offset and correct it in the readings. Right? Both of them are possible. Sometimes the instrument have a way to make it 0. If you have a kitchen scale, you may have noticed without any weight, sometimes it shows a value, not 0, so show a certain value. Then you have a small node to scale it, offset, set the offset and bring the scale to 0. In digital scales, you have something called a tare button. So by pressing the tare button, you make sure that value is set to 0. Right? So like that, you have set a 0 offset. If you don't, you will get an error. We have physical variations and parallax and things like, for example, if you are taking a measurement from a meter stick, if you don't look at it, you'll have the predict. Means there's a small difference between the actual value and the value you are measuring because your eye is not properly aligned. Right? So if you look at anything with if you look it from a side, you will notice the value slightly different because there's a difference. There's a distance between the needle and the gauge. Sorry, dial face. And when you look at it from the angle, you're actually offsetting the value. You are reading a slightly different value, right? So that is called a parallax. So like that, there are many. Okay, we have another slide as well. We have many different poses. You can have instrument drift as well. So this happens because some instruments with time, the values shift slightly. You might have seen in things like oscilloscope and multimeters, even in scale, they have a calibration certificate. I don't know whether you have seen it. They have it. So the calibration certificate they have, this is the date they calibrate. This is the next day you should calibrate. Maybe in 5 years or 3 years, they put another date saying you have to send it to the company to recalibrate it. Because sometimes the values are different. Certain manufacturers give a table. If you measure a value within 6 months from the calibration, this is the amount of error you might get. If you use the instrument after 1 year, this is the amount of errors you might expect. After 2 years, this is the amount. After 5 years, this is the amount. And then you have to calibrate it, right? Some details are provided. You have the and the hysteresis. Let's say you are measuring the temperature of a certain liquid. If you are in a hurry and if you look at the reading, if you take the reading before the thermometers properly reach the equilibrium, you will be reading a lower value, right? Because you know the thermometer gradually show the values in an increasing manner. So if you are in a hurry and if you didn't wait enough time, you might read a lower value. Little bit later, the actual value might be a bit higher. That's one thing. Hysteresis means sometimes one reading or one experiment affect the next repeated time. Time you are doing it, the earlier one can have an effect. Let's say you have an electromagnet. You know electromagnet is, right? And when you send the current, it becomes magnetized. And when you stop the current, magnetic field is gone. That is the theory. But let's say in this instrument, inside the electromagnet, we call it as the core. Core is made from, let's say, stainless steel, or let's say steel or iron. So when you send the current for the first time and make the reading, you get a value. When you stop it, a little bit of magnetism will be left in that iron core. It had become magnetized. So next time when you take the reading, you are actually reading the previous magnetic field plus whatever the new magnetic field you created by the current. So that is called the hysteresis. First time you send the current, it has a certain effect and it lasted until the next reading. So the next reading got affected because of the earlier experiment. So that is called the hysteresis. Sometimes that can happen. And of course, you can have personal errors like carelessness. And sometimes people want to get a certain result. They consciously or unconsciously make certain mistakes. So like that, there are different causes of errors. Right? So look, be careful about these errors and try to avoid them. Right. The previous slides are about some general understanding about the errors. Now we are going to move into a little bit to mathematics side. So if you make a measurement, now we know there should be an uncertainty associated with it, right? You are not perfect, your instrument is not perfect, your measurement is not perfect. There will be a certain amount of uncertainty. That means there will be a certain amount of error related to it. So how are we going to write it? How are we going to use it in the calculations? How is it going to affect our final result? So that's what we are going to look at it. For example, let's say someone says this pencil is 8 centimeters long. 8 centimeters long. For everyday scenario, that is okay. But for science, it's not enough. So when he say 8 centimeters, does it exactly 8 centimeters? Or can it 8.1? Or can it be 8.001? Right? Did he measure it with a meter stick or a vernier caliper or maybe a screw gauge or some kind of instrument that has very high precision? We don't know. So when he say 8 centimeters, can it be 8.1? We don't know. So we have to be careful when you are writing our results. We have to include the uncertainty with it, with the reading. That way, people know how good your reading is. People know how good your reading is. Right? So uncertainty allows the other people to make judgments about the quality of the experiment and compare it with other results and predictions. Right? So that's the idea. So let me tell you another story, not a story, actually a made up scenario, because I can't remember the exact experiment related to this one. I think it's related to general relativity. I can't remember the exact scenario. So I'm going to simplify it and put some arbitrary numbers for you to tell. Let's say there are two research groups. The first research group do a certain experiment. Let's say measure something, right? Measure a weight or something, I don't know. And they say the weight of this particular molecule or whatever the thing is, let's say 12 units. Put whatever the units you like, gram or milligram or whatever, 12. Then another group conduct the same experiment. In science, we repeatedly conduct the same experiment, right, to validate it. And they come up with a value of 13. They come up with a value of 13. Now, can we say one of these groups have made a mistake? Because the values are different. One group says it's 12, another group says no, value we measured is 30. Can we say maybe the group A is wrong or maybe the group B is wrong? Can we say that? We can't. Because we know the uncertainty. Let's say you have uncertainty about 1 unit. So when the first group say value is 12, they are saying, okay, the mean value is 12, but it can be either 13 or 11, somewhere within that range, but the most likely scenario is 12. So when the second group repeat the experiment, they might also have uncertainty of 1. Then what they are saying is, my value is 13, but it might be actually a little bit higher or lower than that. So it can be either 14 or 12. So if that is the case, you realize now the both experiments might be actually correct, or the results got by the both experiments might agree with each other. Why? Because there's a common region and overlapping. Right? So let me draw it and show it to you so that it might be a little bit easier for you. So let's say this is scene A. So measure a value of 12. So this is their reading, but they have an error of 1 unit. So the value can be anywhere within this range. It can be either 13 or 11. So it can be either. No, I tell you, I will little bit tell you what this plus or minus means. It can be anywhere within this range. Now the second group says their values, let's say not 13, let's say 13.5. Their reading is 13.5, but their method also have a possibility of having a 1 unit error. So their value will be somewhere like this. 12.5 might be the least value they can get, or 14.5 might be the value they get. So now you can see in this scenario, you have particular overlapping. So you can't say one group is wrong. In reality, both of these groups might have conducted the experiment correctly. Right? So first group say 12, others say 13.5, but there's an uncertainty. So when you consider the uncertainty, it seems okay. But let's look at another scenario. Let's say again, the first group, a different experiment, take a value of 12. But now they say, we have improved our experiment equipment and setup. So now we can measure it up to 0.1 accuracy. So that means the value they expect is either 12.1 to 11.9. They say the most likely value is 12, but it can range within this range. And let's say in here, same scenario, 13.5. But now the highest you can go is 13.6 or 13.4. Now, do you think in the second case, this is the second case. Now, in the second case, do you think these experiments are matching with each other? Are they tallying with each other? What do you think? Do they agree with each other? Experiment A and B. Yes? No? Maybe? No, right? Because according to this accuracy, don't have any common region. Something has gone wrong. Either experiment A is correct or B is correct. But both of them can't be correct. But in earlier case, both of them can be accurate. So again, let me put another example. Let's want to measure a weight of a coin, 1 rupee coin. Now, in your home, you have, let's say, a kitchen scale. a very bad kitchen scale. And this kitchen scale can measure the accuracy is around, let's say, 10 grams, right? So values are shown from the accuracy is around 10 grams. So values can be either higher or lower by 10 grams. So you measure the 10 rupee coin, 1 rupee coin, and you get 13 grams. Your friend make the measurement and he gets, let's say, 16 grams. Let's say you're using this kitchen scale. So what do you think? Can you say that first, this is your first coin and your friend's coin? Do you think you will agree with your friend? What's the problem with the measurement? Sorry, do you agree with your friend? Do you think the values are telling with each other? You have the kitchen scale, you put a coin. And this kitchen scale only accurate up to 10 grams. You measure it and you get 13 grams per coin. Your friend measure another 1 rupee coin and he says 16 grams. But remember, the kitchen scale can only measure up to plus or minus 10 gram accuracy. Then what can you say? So the error is that higher. 13 grams means this can be either 23 grams in the range 3 grams to 3 grams. This can be from 26 to 6 grams. Now what can you say? Well, we don't know. Maybe it's the same coin, maybe it's a different coin, because you have a common area. Maybe the correct value is 15. Due to the error of the scale, first time it showed only 30. So the correct value is 15. Due to the error of the scale, next time it showed 60. So the actual value is the same. So this can happen. On the other hand, if you measure it using a, let's say, a jewelry scale, where it can measure up to 0.01 gram accuracy, then you have an issue. Because when it says 13, that means it's almost 30. Either 13.001 or 12.99 something. And when you measure 16, the same thing. Right? So that's the importance of uncertainty in experiments. Without the uncertainty, we don't know whether the values are agree with each other or not. We don't know the quality of the experiment. We can't compare the experiments, right? Did you get the idea? එක තේරුණාද? තේරුණේ නැත්තම් කියන්න. Is it okay with you? Okay, there's another request. Can you explain the Sinhala? සිංහලෙන් පොඩ්ඩක් කියන්න පුළුවන්ද කියලා අහන්න බලමු. හරි, මෙහෙම හිතන්නකෝ. ඔන්න අපි දැන් මොන වගේ එකක්ද අපි එකට ගන්න වෙන උදාහරණයක් අපි හිතමු. අපි හිතමු අපි මොකක් හරි දෙයක් දුරක් මනින්න යනවා. Okay? So you are going to measure, let's say, length of a pencil. පැන්සලක දිග මනින්න යනවා. පැන්සල් දෙකක් තියෙනවා. මේකේ දිග පැන්සලක දිග මනින්න යනවා කියමුකෝ. ඔයගොල්ලෝ කාව හොඳ අඩි රූලක් නැහැ. තියෙන අඩි රූල අපි හිතමු අන්තිම සෙන්ටිමීටර විතරයි මනින්න පුළුවන්. මිලිමීටර නෑ. මිලිමීටර ටික මැකි. නෑ නැත්තම් මෙහෙම හිතමු. අඩි රූලක් මේ එකම පැන්සල යාළුවෝ දෙන්නෙක් මනින්න යන්නේ. යාළුවෝ දෙන්නගෙම අඩි රූල් වල පොඩි පොඩි ප්‍රශ්න තියෙනවා. එක්ක මිලිමීටර ටික ගෙවිලා නැත්තම් පොඩ්ඩක් දික් වෙලා හැදිලා උන් ප්‍රශ්න ටිකක් තියෙනවා. හොඳ ප්‍රශ්නයක්. ඇටෙන්ඩන්ස් ෂීට් එකේ ලින්ක් එක තියෙනවද කියලා ලින්ක් එක තියෙනවා පොඩ්ඩක් මම දැන් දාන්න. දැන් අපි හිතමු දැන් මේ අඩි රූලේ ප්‍රශ්න ටික හින්දා ඔයගොල්ලෝ දන්න මැන්නාව සෙන්ටිමීටරයක් විතර එහා මෙහා වෙන්න පුළුවන්. මේ සාමාන්‍ය මීටර රූලක් අඩි රූලක් නෙමෙයි. මේ හොඳටම සවුත් වෙච්ච අඩි රූලක්. ඒකින්ද මේකේ අර මැන්නාම සෙන්ටිමීටරයක් විතරම එහා මෙහා වෙන්න පුළුවන්. දැන් ඒ කියන ළමයා මේ පැන්සල මැනලා කියනවා හරි මගේ පැන්සලේ දිග සෙන්ටිමීටර් 6.4යි සෙන්ටිමීටර් 6 මිලිමීටර් 4යි සෙන්ටිමීටර් 6 මිලිමීටර් 4යි හැබැයි මගේ අඩි රූල එච්චර ෂුවර් නෑ ඒකින්ද සෙන්ටිමීටරයක් විතර එහා මෙහා වෙන්නත් පුළුවන් B කියන ළමයා එයත් අරක මනිනවා මැනලා එයා කියනවා මට නම් ආවේ සෙන්ටිමීටර් 6.8යි හැබැයි මේ මං ගාව තියෙන අඩි රූල හින්දා මටත් සෙන්ටිමීටරයක් විතර එහා මෙහා වෙන්න පුළුවන්. දැන් එතකොට මේ ළමයි දෙන්නගේ රීඩින්ග්ස් වල නැත්තම් ගතු පාඨාංක වල වෙනසක් ඒ කියන්නේ නොගැලපීමක් තියෙනවද නැත්තම් මේක වෙන්න පුළුවන් දෙයක්ද? කාට හරි නැත්තම් කවුරු හරි අතින් වැරද්දක් වෙලාද? ඔය ළමයි දෙන්නගෙන් කාගේ හරි. මොකද හිතන්නේ? දෙන්නගෙන් පාඨාංක දෙක සමහරට ගතු දෙක ඇත්තටම හරි වෙන්නත් පුළුවන්. මම කියන්නේ මේ අඩි රූල ඇත්ත දිග නෙමෙයි ගතු පාඨාංක දෙක දිහා විතරක් බලලා කියනවනම් මේ දේ වෙන්න පුළුවන්ද? එක්කෙනෙකුට 6.4යි අනිත් එක්කෙනාට 6.8යි එන්න පුළුවන්. So what I was explaining was there was a pencil. Two students measured the length of the pencil, but the measuring rule is not good. They can have an error of 1 centimeter. First student gets 6.4, second student gets 6.8. Can this happen? Make a venna puluwanda. Venna puluwan, right? මොකද සෙන්ටිමීටර එක error එකක් තියෙන පුළුවන් කියලා කිව්වනේ. ඒතකොට 6.4 මනිද්දී සමහරට ඇත්තටම තියෙන ගානට වඩා අඩු වෙන්නත් පුළුවන් වැඩි වෙන්නත් පුළුවන්. ඒතකොට ඒ දෙන්නගේ මෙෂර්මන්ට් දිහා විතරක් බලලා මට කියන්න බෑ ස්ටුඩන්ට් B වැරදි නැත්නම් ස්ටුඩන්ට් A වැරදි නැත්නම් දෙන්නම වැරදි මුකුත් කියන්න බෑ. දෙන්නම හරියන්නත් පුළුවන්. දැන් ඕකම හිතන්න ඔය දෙන්නගේ දැන් අර පරණ මීටර් රූල් දෙක අයින් කළා මම දෙනවා අලුත්ම මීටර් රූලක්. මේක මනින්න පුළුවන් මිලිමීටර් භාගයට. පළවෙනි ළමයා පැන්සල මැනලා ආයි පාරක් කියනවා මට එන්නේ මේ සෙන්ටිමීටර් 6යි මිලිමීටර් 4යි. මගේ මීටර් රූල් මගේ සෙන්ටිමීටර් මගේ මේ මනින රූල් එකෙන් පුළුවන් මිලිමීටර් 0.1කට මනින්න 0.1 මිලිමීටර වෙනකන් හරියට මනින්න පුළුවන් මීටර් රූලක් නෙමෙයි වෙන එකක් හිතා ගන්න කැලිපරයක් හරි මොකක් හරි මනින්න පුළුවන් දෙවෙනි ළමයාටත් මේ එයාගේ මීටර් රූල් අපි අලුත් එකකට ඉම්ප්‍රූව් කරනවා ඒකත් පුළුවන් 0.1 මිලිමීටර බලන්න එයා බලලා කියනවා මම මෙන්නහම ආවේ මිලිමීටර් සෙන්ටිමීටර් 6යි මිලිමීටර් 8යි කියලා දැන් ওই දෙකම වෙන්න පුළුවන් පළවෙනි කරට 6.4යි දෙවෙනි කරට 6.8යි හැබැයි දෙන්නක මීටර වලින් 0.1 මිලිමීටර ඇකුරේට මනින්න පුළුවන් වෙන්න පුළුවන්ද
වෙන්න බෑ
වෙන්න බෑ කොයි හරි ප්‍රශ්නයක් එක ස්ටුඩන්ට් කෙනෙක් වරද්දලා මැනලා තියෙනවා right එතකොට මම කොතනදි හරි කිව්වොත් මීටර රූල ගැන කතා කරන්නේ නැතුව එක ළමයෙක් මැන්න එයාට ආව 6.4ක් අනිත් ළමයා මැන්න 6.8ක් ආවා කියලා මට එකකින් වැඩක් ගන්න පුළුවන්ද මේ දෙක සමානද වෙනස්ද දෙන්නම හරිද දෙන්නම වැරදිද මුකුත් මට හිතා ගන්න පුළුවන්ද මීටර් රූල ගැන මෙෂර්මන්ට් අන්සර්ටනිටි ගැන කතා කරන්නේ නැතුව එර එක ගැන කතා කරන්නේ නැතුව නිකන් නියම නමට විතරක් කිව්වොත් රිසල්ට්ස් දෙක විතරක් කිව්වොත් වැඩක් තියෙනවද
නෑ
වැඩක් නෑ
වැඩක් වෙන්නේ
අපිට හිතා ගන්න බෑ මේ මෙෂර්මන්ට් දෙක ටැලි වෙනවද මේ දෙක එකට ගැලපෙනවද මේ පාඨාංක දෙක නැත්නම් මේ දෙක වෙනස්ද මේක කොච්චර ක්වොලිටිද මේ 6.4යි කියන්නේ මේ කිලෝමීටරයක් මනින්න රූලකින් මනලාද නැත්නම් මේ මයික්‍රෝමීටර මනින්න පුළුවන් රූලකින් මනලාද කොච්චර ඇකියුරසිද ඒ මොකොත්ම හිතා ගන්න බෑ ඒකයි අර අපි පාඨාංකයක් ලියනකොට අපි uncertain එක දාන්නේ right so that's why we put uncertainty when we are writing with a measurement that gives you a way to compare it with others to find the quality එක කොච්චරද මේක කොච්චර නිවැරදි පාඨාංකයක්ද කියලා මනින්න පුළුවන්කම තියෙන්නේ මේකේ for example I remember long time ago we were doing an experiment I think long time ago a student was doing an experiment to find the gravitational acceleration g one experiment එකක් තියෙනවනේ he got 9.8 something accurate up to 2 decimal places but error is I think 2 ඒ කියන්නේ value එක ඇවිල්ලා තියෙන 9.88යි කියලා හැබැයි error එක තියෙනවා දෙකක් ඒ කියන්නේ අර 9.88 ලොකු වැඩක් වෙලා නැහැ error එක දෙකක් තියෙනවා කියන්නේ ලොකු range එකක වෙන්න පුළුවන් ඒකට ඒ experiment එකෙන් ලොකු ප්‍රයෝජනයක් ගන්න බෑ value එක හරියට ආවට uncertainty එක වැරදි නම් ප්‍රශ්නයක් වැඩි නම් ප්‍රශ්නයක් right now let's move to the next slide here now I told you so when you are writing a reading we have to put the best estimate for the reading and the uncertainty but the problem is how do you know the uncertainty what is uncertainty how do you know the error now I think I might have confused you a little bit without actually understanding it now the term error and uncertainty are two different things I should have mentioned it earlier error means the actual difference between the correct value and the real correct value and the value you measured uncertain is a little bit slightly different meaning I'll come to that later so if you want to calculate the error you have to know the correct value and the measured value and find the difference error එක මොකක්ද කියලා අහුවොත් මොහොකාරයි අපි හරි value එකෙන් ආපු value එක අඩු කරලා වෙනස කියන්න වෙනවා ඒක තමයි error එක ඒ කියන්නේ අපේ G ප්‍රශ්නය නම් හරි value එක 9.8යි මට ඇවිල්ලා තියෙන 9.9යි එහෙනම් error එක 0.1 සාමාන්‍යයෙන් error එක calculate කරන්නේ එහෙමයි this is how you calculate the error you have the correct value then you have the measured value the difference between them is the error ඒක තමයි error එක එන්නේ හැබැයි දැන් ප්‍රශ්නයක් එනවා now you have a problem because to calculate the error you have to know the correct value right But if you know the correct value, you don't have to measure it, right? If you know the correct value, you can directly go ahead and use it. අපි error එක කියන්නේ හරි එකෙන් අපි measurement එක අඩු කරාම වෙනස. වැරද්ද. හැබැයි හරි එක දන්න ඕන නම් ආයි ඉතින් measurement එකක් ගන්න ඕනේ එකලිම ලියන්න පුළුවන්. Right? So the scenario, actual scenario is we do not know the correct value. We don't know the correct value. We only have an estimate. We estimate this should be the correct value. This should be the best value matching our scenario. Right? And compared to best value, this is the amount of uncertainty or the range you can have. ඒ කියන්නේ ඔතන වචන තුනක් තියෙනවා පටලව ගන්න එපා. එකක් තමයි correct value. හරිම value එක, right? Correct value එක කියන්නේ ඇත්තම value එක. ඒක measurement එකකින් ගන්න අමාරු. ඒක theoretical value එකක් හරි වෙන මොකක් හරි ක්‍රමයකින් ආපු එක. Right? First one is the real value. It's hard to take from a measurement. Maybe you can get some idea from a very good measurement, but mostly comes from a theoretical value or something. Correct value. Error means the difference between the correct value and your reading. ඒ කියන්නේ අපි පැන්සල නම් අපි දන්නවා කොහොම හරි හරියට මේක සෙන්ටිමීටර 8යි තියෙන්නේ. නිකන් දෙවියෝ කියලා වගේ දන්නවා. 8යි තියෙන්නේ. මැන්නාම වෙනවා 8.1. එහෙනම් error 1.1යි. Somehow we know this pencil is 8 centimeters long, and when we measure it, we get 8.1. Then the error is 0.1. But this approach has a problem. දැන් මේකේ ප්‍රශ්නයක් තියෙනවා. මොකද හරිම value එක මම දැන් ඉබේ ආවා වගේ නේ කිව්වේ. එහෙම එකක් එන්නේ නැහැ සාමාන්‍ය එක්ස්පෙරිමන්ට් කරද්දී. මොකද හරිම value එක දන්නවනේ එක්ස්පෙරිමන්ට් එක කරන්න ඕනේ කෙලිම value එක දාන්නනේ. Right? So we have a chicken and egg problem. To calculate the error, we have to know the correct value. But if we know the correct value, we don't need the error. Error එක හොයන්න නම් ඇත්ත value එක දැනගන්න ඕනේ. ඒකත් එක්කනේ measurement එක compare කරන්න. හැබැයි ඇත්ත value එක දන්නවා නම් ආයි measurement එකක් ගන්න ඕනෙත් නැහැ. error එක හොයන්න ඕනෙත් නැහැ. So the real scenario is most of the time we don't know the correct value. අපි ඇත්තම value එක අපි සමහරට දන්නේ නැහැ. ගොඩක් වෙලාවට දන්නේ නැහැ. Instead, we have a best estimate. For example, you have this pencil. You ask people to, let's say, five students to measure the length. Or maybe you take five different readings and come up to an estimate. Okay. From all this reading, I can say this pencil is most likely 8 centimeters long. Most likely 8 centimeters long. My best estimate for the length of the pencil is 8 centimeters. මේ ගත්තු readings අනුව මට කියන්න පුළුවන් මේක සෙන්ටිමීටර් 8ක් තමයි හොඳම estimate. මම හිතන විදිහට මේක සෙන්ටිමීටර් 8යි. මේ හරියට මටයිද කියන්න දන්නේ නැහැ. නමුත් මේ measurement අනුව මේක 8ක් වෙන්න ඕනේ. So that is the best estimate. And then you give the uncertainty. හැබැයි සෙන්ටිමීටර් 8ක් වුණාට මිලිමීටරයක් නැත්නම් අපි මිලිමීටර් 2ක් අඩු හෝ වැඩි වෙන්න පුළුවන්. මට තේරෙන විදිහට මේක සෙන්ටිමීටර් 8යි දිග. ඒක තමයි වෙන්න පුළුවන් හොඳම ගානේ. ගොඩක් වෙලාවට සෙන්ටිමීටර් 8ක් වෙයි. හැබැයි මිලිමීටර් 2ක් විතර අඩු හෝ වැඩි වෙන්නත් පුළුවන්. ඒ රේන්ජ් එක ඇතුලේ තියෙනවා කියලා මම දන්නවා. So best estimate means you can say, okay, from the readings or the measurements, I can say, or I can estimate this is to be 8 centimeters, but it can be either 2 millimeters longer or shorter than the 8 centimeters. So it can be anywhere within that range, but my best estimate is 8 centimeters. තේරුණාද? නැත්තම් මෙහෙම කියමු. ඔන්න දැන් ඔයගොල්ලෝ බස් වෝල්ට් එකේ වෙලා ඉන්නවා බස් එකක් එනකම්. දැන් අපි දන්නවා බස් ස්ටෑන්ඩ් එකකින් ওই බස් එක පිටත් වෙන අපි දවල් 12ට කියලා උතන්ට එන්න විනාඩි 10ක් 15ක් යනවා. ඒකට ඔයා කියනවා හරි. යාළුවෙක් අහනවා දැන් ඊළඟ බස් එක එන්නේ කීයටද? ඔයා කියනවා 12යි 10 වගේ වෙයි. හැබැයි ඉතින් විනාඩි 5ක් විතර එහා මෙහා වෙන්නත් පුළුවන්. දොළහයි 10 විතර වෙයි. That's the best estimate. ඒක තමයි best estimate එක. හැබැයි විනාඩි 5ක් විතර එහා මෙහා වෙන්නත් පුළුවන්. ඒ කියන්නේ හැබැයි 12යි 10යි කොට 12යි 5ට එන්නත් පුළුවන් 12යි කාලට එන්නත් පුළුවන්. හැබැයි ඒකෙන් එළිය එන්නේ නැහැ. ඒ කියන්නේ පැය භාගයක් විතර වගේ පරක් වෙලා එන්නේ. එහෙනම් ඒ වෙන බස් එක. So like that, when you have a measurement, you put the best estimate plus an uncertainty. දැන් බස් එක ඇත්තටම ආවට පස්සේ එර එක හොයන්න පුළුවන්. ඒ යාළුවා කරන 12යි 10ට විතර එනවා කියලා බලන් ඉන්නම් 12යි 12ට විතර එනවා. අන්න එතකොට අපි එර එක දන්නවා. මම එනවා කියේ 12යි 10ට හැබැයි ආවේ 12යි 12ට. ඒ කියන්නේ විනාඩි දෙකක එර එකක් තියෙනවා. හැබැයි එර එක හොයාගත්තේ ඇත්තටම බස් එක ආවට පස්සේ. ඇත්ත එක දන්න හින්දා. ඇත්ත එක දන්නේ නැත්නම් අපිට කියන්නේ හොඳ ගොඩක් වෙලාවට මේක තමයි එන වෙලාව 12යි කාල 12යි 10 තමයි එන වෙලාව. හැබැයි පොඩ්ඩක් එහා මෙහා වෙන්න පුළුවන් මෙච්චර විතර ගන්න. right? So that's the idea. ඒක තේරුණාද? estimate එක uncertainty එකයි වෙනස. වෙනස නෙමෙයි ඒක පාවිච්චි කරන්නේ කොහොමද කියලා. Is it clear? Good. Right. Now that uncertainty you can give in different ways. You can give it as a number or as a fraction. Right? So if you're giving it as a fraction or a percentage, we call it as relative uncertainty. සමහරට ඒක ප්‍රතිශතයක් නැත්නම් අනුපාතයක් විදිහට දෙන්නත් පුළුවන්. මේක තමයි ගාන හැබැයි 105ක් 101ක් දෙකක් එහා මෙහා වෙන්නත් පුළුවන්. So that's what the relative uncertainty means. So this is how you calculate it. You get the uncertainty and divide it by the measured quantity. And you take the absolute value. Now uncertainty can't be negative. It has to be a positive value. So you have to take the absolute value. Here we have, this is how you write a measurement 75.5 grams plus or minus 0.5 grams. So if you want to calculate the relative uncertainty, you divide 0.5 by 75.5. And actually you have to multiply by 100 if you put in a percentage sign. If you are not putting the percentage sign, you can just divide and put the value. මෙතන ප්‍රතිශත මාර්ක් එක දානවා නම් ඇත්තට මේ 100න් වැඩි කරන්න ඕනේ. ඒක පොඩ්ඩක් මේ ඉක්වේෂන් එක පොඩි ප්‍රශ්නයක් කරලා තියෙනවා. ප්‍රතිශතය නැතුව නිකම් අනුපාතයක් විදිහට දක්වනවා නම් මේක කෙලින් බෙදලා දාන්න පුළුවන් percentage sign එක දාන්නේ. That's the way you calculate relative values, right? ඒක සාමාන්‍ය කළා තියෙනවනේ ස්කෝල වල එහෙම. Right? Then we come to another important topic, how to write your measurement. Now we talk about the two important things. The errors you can get when you are making a measurement, why the errors are important, and how you put the uncertainty when you are writing a measurement. But usually we write everything in a scientific notation. There are again different ways. This is the standard normalized form. You write it like this. You write the value with one, what do you call it? You have a fractional part and a complete whole part. In the whole part, you put one decimal place after this one, and rest of the one, to equal it, you have to multiply it by the power of 10, 10 to the power some value. Right? And so 315 becomes 3.15 multiplied by 10 to the power 2. So this M, we put it as between 1 and 10. right? So it has to be a single number, single digit. This has to be a single digit. After that single digit, you have the fractional part multiplied by the exponent. Right? Now, I want you to quickly do, let's say, the first 3 and put the answer in the chat. Convert them into standard notation and put the answer in the chat. But the multiply sign, you can use the letter X or the star. And for the power sign, you can use the hat mark because I don't think in the chat window you can use equations. So use a hat sign or something like that to denote the power. Right? Do the first 3. First 4, because fourth one you have a fractional part. First 4 and put the answer in the chat. concept. So when you are writing a measurement, make sure you convert it to standard notation and also write it with the error. So we'll talk about how to write it with this error. But before going that, we have another important concept to learn that is called significant figures. Significant figures. Now, when you write a number, now a number consists of multiple digits. Some of the digits will be considered significant, some of them will not be considered significant. So, depending on the whether a digit is significant or not, you have to decide how to write the error. So how do you know if something is significant or not? Now, here I'll tell you what are not significant figures, significant numbers. Any leading zeros will not be significant. So instead of writing in letter number 2, if you put 002, the leading zeros are not significant. If you have 005, the first 2 zeros are not significant. And if you have any trailing zeros as placeholders, those are not significant. Especially if you have something like, let's say, 1.50. 1.50. Here you have a trailing zero. The zero is there. If it is a placeholder, it's not a significant figure. But if it is a part of a measurement, you want to tell it, I can measure it up to 0.01 accuracy. So when you say 1.50, it's actually 1.50, not 1.51 or 1.52 or 1.49. It's actually 1.50. That last zero is actually part of the measurement. If that is the case, it is significant. But let's say you just measure it as 1.5, and in the Excel or somewhere you need to have everything in same number of digits. So to fill that requirement, you put some zeros to the end. You're just filling it as placeholders. So those zeros are not part of the measurement. Right? You just put it there because you want to fill that gap. Then those are not significant. Then and any okay. So the first one I think everyone understand. මුලින් තියෙන බිඳු අදාළ නැහැ කියන තේරෙන අන්තිමට කියන බිඳු කතාව මොකක්ද? Now let's say you are doing, you're presenting a budget of a society, or maybe national budget or something. Then he says 3.2 million rupees. Right? Then you put 3.2. Let's say 3.2 million rupees. Then you put 32 and some zeros after that. Now, if your budget is exactly 3.2, those trailing zeros are important. But if your budget is actually 3.216, something like that, you just round it up to 3.2. Then the trailing zeros are just placeholders. They are there to fill the gap. Those zeros doesn't actually mean zero value. They are there just because you round it up and you have to have the same number of digits there. In that case, they are not significant. And you can have spurious digits. So sometimes you do the calculation and your answer comes with more digits than the actual measurement. For example, let's say in your calculation, you have something like this. Let's say you are measuring a weight or taking the average of something. And as a result, somewhere in the calculation, you get something like this, 1/3. Maybe you have 1 kilogram of something and 3 equal units, you want to get the average value. So 1/3, if you write it as a fraction, sorry, if you write it in a decimal form, what will be the value? What will be the value of this one? 0 point what?
33.
33. Is it enough?
No.
No, you have 3. You can put any number of 3s. Let's say this is actually a weight of 1 kilogram, and I don't know. Let's say you are measuring something with 3 equal units, maybe 3 equal iron balls or something. You want to get the average value, average weight of 1 unit. And look in this calculation, you will say, okay, it's 333 grams and 33 milligrams and 33 micrograms. Is it correct like that? Can you say it is 33 micrograms or anything like this? Can you say it like that?
No.
No, because in actual reality, maybe your scale can maybe only measure up to 1 gram. Plus or minus 1 gram, right? So when you have multiple measurements, how to calculate it, I'll teach you in the next lesson. But for this one, what you have to know is it should be around 1 gram, same ballpark. You can't go up to microgram because just because you saw some digits in the calculator. That's again important. Something most students forget. Because when you are doing the calculations in physics and experiments, sometimes you see about 10 digits in your calculator. Don't put it in the answer. Just look at and calculate the error and put only the relevant digits. Just because you have 10 digits, that doesn't mean your answer is correct up to that point. Right? ඉලක්කම් ගොඩාක් තිබුණා කියලා ඒ ඔක්කොම ඉලක්කම් හරි උත්තරේ වෙන්නේ නැහැ. ඔරිජිනල් පටන් ගත්ත error එක තියෙනවා මේකේ දිගටම. ඒකට මේ තුනිය පේලියක් ආව කියලා ඒ තුනිය පේලිය වැදගත් ඒවා නෙමෙයි. ගොඩක් ඒවා අදාළ නැහැ. මේ හරියෙන් ප්‍රයෝජනයක් නැහැ. Right? So those are called spurious digits. That means they are coming as a result but not actually useful. They don't have a value. Right? So those are the cases where values are not significant figures. Digits are not significant. Right? So here how you write a value in scientific notation. We usually round it to one significant figure. Right? And smallest measurement and uncertainty should be comparable. So when you are writing an error, we usually write it with a single digit, one significant figure. Although I use the word digit, the correct value will be significant figure. So this is also a digit, this is also a digit, but this is a significant figure. Up to one significant figure. And if you can use a parenthesis, that will be really useful. Sometimes people don't use them. Sometimes even the textbook don't have them. But without the parentheses, people can get confused. For example, 10 to the power minus 1. Now with the parentheses, we know this whole expression should be multiplied, should be divided by 10. So 10 to the power minus 1 is common to this term and to this term. Without the parentheses, then it can be a little bit confusing. 10 to the power minus 1, is it only for this error or does it include this reading as well? Right? So better to use parentheses. That will save a lot of headaches. So those are the three important things. Now you know how to write the scientific notation. We learn it. So the first part is about that. But now with the scientific notation, we are adding the error. So how do you write the error? Plus or minus whatever the error. And error is usually rounded to one significant figure. We don't put the error as 0.02132, something like that. We don't. We put the error in one significant figure. Most of the time, the smallest measurement and uncertainty would be in the same ballpark, roughly in the same scale. Right? Can be changed, but most of the time in your level, that would be the case. And using the parenthesis is a good idea. Okay. Next, we have multiple measurements, but I think we can shift it to the next day because now we are shifting to another topic. When you have 10 different readings, how are you going to calculate the error? Things like that. You already know how to calculate the average value, but what will happen when you have the error? Right? Those things we will cover in the next stage. Because today I'm going to talk about the statistical pitfalls that last time I wanted to do one of those things, but we did not have enough time. So today we are going to cover that one. Before going there, any questions you want to ask from today's lecture? මේක කරන්න කලින් මුකුත් අහන්න ප්‍රශ්න ගැටලු මුකුත් තියෙනවා අද කරපු lecture එකේ. So let me quickly recap what we did in the other PowerPoint so you can get an idea. First we learn what is uncertainty and what is precision. I told you a small story so you
Excuse
can
me,
get. Okay, Anupati.
ඔතන සර් ඕක දැන් අරන් තියෙන විදිහට graph එකේ කොහොමද එතන වෙන්නේ?
Okay,
දැන් සර් දැන් උඩම තියෙන එකේ high precision එකේදී low accuracy එකක් කියවනේ. එතකොට අපි ගත්ත අගයන් වලදී accuracy තැන තියෙන්නේ හරි mid point එකේනේ. එතකොට අපිට readings ඇවිල්ලා තියෙන්නේ ඒතරින් පැනපු ඒවා ආවයි කියන එක එතන අර්ථකථන නෙමෙයි.
ඒ කියන්නේ readings ටික ඇවිල්ලා තියෙනවා. readings ටික ඔක්කොම එකට කිට්ටුයි. හැබැයි ඇවිල්ලා තියෙන්නේ වැරදි readings ටික. ඒක වෙන්නේ කොහොමද කියලා දහන්නේ? ඔව් ඒ කියන්නේ හිතන්නකො දැන් අර බර කිරණ තරාදිය එක පැත්තක් තට්ටුවක් බර වැඩි කියලා. තරාදිය හොඳට වැඩ. ගානට කටුව බැලන්ස් කරනවා හැබැයි එක තට්ටුවක් බර වැඩි. ග්‍රෑම් 100ක් වැඩි නම් හැමතිස්සෙම ඒ ග්‍රෑම් 100 වැඩි වෙනවා. එතකොට 100 මනින් හැම පාරම 900 900 900 එක දිගට එන්නේ. එතකොට values කිට්ටුයි හැබැයි එන්නේ වැරදි කරට.
හරි සර්.
Right? Right? So we learn about precision and accuracy and how they affect with each other. And we learn there's something called uncertainty. So it's a combination of both accuracy and precision. And uncertainty is associated with the measurement. Uncertainty. And there are two different types of errors, random errors and systematic errors. I told you the causes of these errors and how to detect them and how to correct them. Random errors what to do and systematic errors what to do. And here are some causes of errors when you are doing an experiment. Definition issues, failure to account for the factors, instrument errors, calibration, offset, like that. We talked about different causes of errors. And what is the importance of uncertainty in a reading? Uncertainty right? So we discuss where it comes into play. It gives you a way to compare two results. It gives you an idea about the quality of the experiment, right? And without uncertainty, readings really do not have any meaning, right? When you say its result is 8, that doesn't give you any idea whether it's a high precision result, whether it's highly accurate. We have no idea. So we usually write it with the error. Sorry, with the uncertainty. So here error is the difference between the real value and the measured value. Uncertainty is basically giving you a range of what the possible values can be, and the readings you are getting is called the best estimate. So a measurement consists of an estimate and an uncertainty followed by units. බස් එකක් යනකම් බලන් හිටපු කතාව වගේ තමයි කියන්න වෙන්නේ. measurement එකක් කියන්නේ estimate එකයි uncertainty එකතු කරලා එන්නේ. And you can measure the uncertainty in the relatively as well as a fraction or as a percentage. And when we write a measurement, we write it using scientific notation. And we learn about significant figures and how to write a measurement with the error. Sorry, with the uncertainty. So those are the things that we covered. So let's go to today's one. Right. Now, here I'm going to talk about some everyday nice scenarios. Again, this is full of stories. Make samane katandara dina kaya.
Excuse me, sir.
Yeah, Anna.
Sir, මේ අර දැන් ස්ටෑන්ඩඩ් නොටිෆිකේෂන් වලදී දැන් සර් අර දාපු එකේ තිබ්බා 315 කියන එකක් තිබ්බා අනිත් එකේ තිබ්බා 315.00 කියලා. එතකොට ඒකේ දැන් ස්ටෑන්ඩඩ් නොටිෆිකේෂන් ලියද්දී 315 තියෙන එකේ 3.15 වැඩි කිරීම 10 දර්ශකයන් ලියවින් මේකට අග බිංදු දෙක නොසලකා හරිනවා.
Right. Antima example එක නේද? ඒකේ එතන හැබැයි මට පොඩි විස්තරයක් කරන්න තිබ්බා මේක measurement එකෙන් ආපු එකද නැද්ද කියලා. මේක measurement එකකින් ආපු එකක් නෙමෙයි නම් අග බිංදු දෙක නොසලකා හරින්න පුළුවන්. නමුත් ඇත්තටම මේ මැන්නහම බිංදු දෙකක් නම් ආවේ. මැන්නහම බිංදු දෙකක් ආවා නම් හලන්න බෑ. ඒ කියන්නේ අපිට 315 කියලා මැන්න මොනවා හරි. හැබැයි උත්තරේ ලියනකොට දකින්න අර ටේබල් එකේ හරි කොහේ හරි මේක දශම ස්ථාන දෙකකට ලියන්න ඕන. නැත්නම් අපිට රුපියල් වලින් කියලා මැන්නේ. රුපියල් 315යි. මෙහෙම දෙයක් හිතමු. බැංක් මේ කාසිය නෙමෙයි අපි බැංක් එකේ account එක කියලා interest එක calculate කරනවා. calculate කරාම කවුරු හරි අහනවා ෆෝන් එකකින් හරි මේ මගේ account එකේ කීයක් තියෙනවද? එතකොට ඇත්තටම account එකේ තියෙන 315යි 7.0.0යි නම් 7.0.0යි කියන එක එතනදී වැදගත්. මොකද ඇත්තටම තියෙන 7.0.0 මැනලා තියෙනවා 7ටම ඒක significant. නැත්තම් හිතමු 315යි තව 7 ගණනක් තියෙනවා. කියන්න ලේසියට 7 ගණන හරලා කියනවා නෑ 315යි තියෙන්නේ. එතකොට මොකද වෙන්නේ? අර ලියනකොට 315යි කියලා අර ලියන්න ඕනේ හින්දා දශම ස්ථාන දෙකකට 7 දානවා. හැබැයි දශම ස්ථාන දෙක මැනලා නෙමෙයි අරන් තියෙන්නේ. අන්තිම රුපියලට විතරයි ගාන හදලා තියෙන්නේ. 7 ගැන හොයලා නැහැ. 7 මැනලා නැහැ. දාන්න ඕනේ හින්දා බිංදු දෙකක් දාලා තියෙනවා. එහෙම දාන්න ඕනේ හින්දා නැත්තම් ෆෝමැට් එකට ඕනේ හින්දා නැත්තම් ෆිල් කරන්න ඕනේ හින්දා ප්ලේස් හෝල්ඩර් එකකින් දැම්මා නම් ඒක සිග්නිෆිකන්ට් නැහැ. ඒ බිංදු දෙක හලන්න පුළුවන්. මොකද ඒ බිංදු දෙක කිසි වැදගම්මක් නැහැ. නිකන් අර ලස්සනට ලියන්න ඕනේ හින්දා හරි මේ දශම ස්ථාන ගන්න තියෙන්න ඕනේ හරි පෙනුමට තියෙන්න ඕනේ හින්දා හරි දාපුවා. ඒවා සිග්නිෆිකන්ට් නැහැ. සිග්නිෆිකන්ට් කියන්නේ වැදගත්. සාමාන්‍ය සිග්නිෆිකන්ට් කියන්නේ වැදගත් නේ. ඒක වැදගත් නැහැ. ඒක නිකන් අර කරන්න දෙයක් නැතුවට දාපුවා. හැබැයි 7ටම බලලා බැලුවම ඇත්තටම තියෙන බිංදුවක් නම් ඒක වැදගත්. මොකද ඒ ඇත්තටම මැනලා ගත්තු රිසල්ට් එකක්. ඒකේ ඇකියුරසි එක වැඩි. ඒ බිංදු දෙකෙන් කියන්නේ අන්තිම 7ටම මැන්න කියලා. තේරුණාද වෙනස? එතන මම ඒ කියන්න තිබ්බා මේක මෙෂර්මන්ට් එකෙන් ආපු එකක්ද නැද්ද කියලා. මේ තියෙන විදිහට හරියට හිතා ගන්න අමාරුයි. මට හිතෙන්නේ නම් ඉතින් නෑ ඒක හරියනම් කියන්න ඕනේ. මෙෂර්මන්ට් එකෙන් ආපු දශම ස්ථාන දෙකක්ද ප්ලේස් හෝල්ඩර් එකක්ද කියලා. ප්ලේස් හෝල්ඩර් එකක් නම් හලන්න පුළුවන්. සිග්නිෆිකන්ට් නෑ. මෙෂර්මන්ට් එකෙන් ආපු එකක් නම් හලන්න බෑ. ඒක සිග්නිෆිකන්ට්. තේරුණාද?
සෝ එතකොට සර් ඒක දැන් ස්ටෑන්ඩඩ් නොටිෆිකේෂන් වලින් ලියද්දී 3.15යි වැඩි කිරීම 10 දෙකක් කියලා ලියන්න බෑනේ.
සිග්නිෆිකන්ට් නෙමෙයි නම් 315යි 3
ස්ටෑන්ඩඩ් නොටිෆිකේෂන්
ස්ටෑන්ඩඩ් ලියන 3.15 ඊට පස්සේ සිග්නිෆිකන්ට් නම් ඔයාලට 0.0 දාන්න පුළුවන්. සිග්නිෆිකන්ට් නැත්තම් ඒක හලලා දාන්න පුළුවන්.
හරි සර්.
තේරුණාද? ඒ කියන්නේ දැන් සාමාන්‍යයෙන් අපි දශම ස්ථාන අගට බිඳු දාන්නේ නැහැ. ඒකෙන් උතන හරි ගැටලු වෙලා ඇත්තේ. හැබැයි ඇත්තටම මන්නම් 0.0 නම් ආවේ. ඒකෙදි ලියන්න වෙනවනේ.
ඔව්.
නැත්තම් අපි මැනපු එකේ අපි නිකන් මැනලා ඒ කැල හලලා නිකන් අපි බාගෙට මැනනවා වගේ අදහසක් නේ. එතකොට එන්නේ මෙයා මිලිමීටර මැනලා නැහැ කියලා හිතුවා. දැන් හදිසියක් 0.0.1 ආවා කියමු. එහෙමනම් අපි අනිවාර්යෙන් 3.150 කියලා ලියනවනේ. මොකද අපි දන්නවා ඒක දැක්කම මිලිමීටරයකට මැනලා තියෙනවා. ප්‍රශ්නේ තියෙන්නේ ඒක නැතුව ඔක බිඳුව ආපු ගමන් මේ බිඳුව තියෙන්නේ මේ ඇත්තටම මැනලා ආපු බිඳුවක්ද නැත්නම් මේ ජොලියට දාපු බිඳුවක්ද කියලා ෂුවර් නෑ. ඒක හොයාගන්න මොකද අපේ සාමාන්‍ය රවුන්ඩ් කරනවනේ නම්බර්ස්. දැන් රවුන්ඩ් කරාම බිඳුව තමයි දාන්නේ. එතකොට බිඳුව වෙන්න පුළුවන් ක්‍රම දෙකක් තියෙනවා. ඇත්තටම මන්නම් බිඳුව වෙන්නත් පුළුවන්. ඒ කියන්නේ සිග්නිෆිකන්ට්. නැත්තම් මේ කරන්න දෙයක් නැතුවට නිකන් පුරවන්න දාපු බිඳුව වෙන්නත් පුළුවන්. ඒක සිග්නිෆිකන්ට් නෑ. හේතුව දන්නේ නැතුව කියන්න බෑ.
හරි සර් හරි thank you.
Hari. Now we are going to talk about statistical pitfalls. Right. Now this one I took from a different country, but in Sri Lanka also we have things like that. Jinx කියලා එකක් අහලාද? Jinx means a belief. Can you remember now? There was a time, there was a particular playground, cricket ground in Sri Lanka. There was a belief that if there's a match in that ground, it's always going to rain. Have you heard about that one? Cricket fans, how many of you are cricket fans? Cricket අහන කී දෙනෙක් ඉන්නවද? මම නම් cricket එච්චර ආස නැහැ මේ ඒකට අනිත් කැමතිනේ. එහෙම එකක් අහලා තියෙනවද? Have you heard? There was one particular ground in Sri Lanka. People used to believe if you have a match on that ground, it will always rain. අහලා තියෙනවද? එහෙම ground එකක් තිබ්බා ඉස්සර. දැනුත් තියෙනවද කියන දන්නේ නැහැ. Anyone heard about that story? Okay, here's a recent one. Right? There was another story that one particular political person, if he goes and watch the match, Sri Lanka will lose the match. Have you heard about that story? එහෙම එකක් අහලා තියෙනවද? ඒක අහලා තියෙනවා කට්ටිය. Right? Those things are called jinx. Jinx means things people believe. Right? So for the first two cases that I mentioned in Sri Lanka, we have not done any statistical analysis. So I don't know whether it's true or not. But the case I'm going to tell you, this one we had done an analysis. So we can tell you about that. If you're interested, you can do the analysis for those two cases as well. Right? මුලින් කිව්ව දෙක ගැන මම statistically analyze කරලා නැහැ. ඒකින්ද ඔයගොල්ලෝ කැමති නම් කරලා බලන්න පුළුවන්. මේක statistically කතා කරපු දෙයක්. So this is the belief. Now, I think this is a US magazine. There's a magazine called Sports Illustrated. So in the magazines, you have a cover page, right? So the idea is, or the belief is, if someone appeared on the cover of this magazine, from the next year onward, he will perform poorly. ඒ කියන්නේ මේ Sports Illustrated කියන magazine එකේ cover page එකේ කවුරු හරි ක්‍රීඩකෙක් සාමාන්‍ය ෆොටෝ එකක් දාන ක්‍රීඩකයෙක්ගේ ෆොටෝ එකක් දැම්මොත් ඊළඟ අවුරුද්දේ ඒ ක්‍රීඩකයාගේ හැකියාව හුඟක් බහිනවා. ඒ ක්‍රීඩකයාට ඊළඟ අවුරුද්දේ දිනන්නම බෑ. කොහොම බිලීෆ් එකක් තියෙනවා. Right? So this is for multiple sports. Okay, this particular magazine. And here's the proof. So this is from Wikipedia. This is the list of people that happen to have this effect. You can see there's a long list. These people appeared on the magazine on this given date, given month, and in the following year or following month, they did not perform well. On the magazine එකේ මේ මාසෙ හිටියේ ඊළඟ මාසෙ නම් performance එක ගන්නම දෙයක් නැති වෙන්න යනවා. මේ තියෙන example. This is examples taken from Wikipedia. You have a long list. I just put a small list. Right? So what do you think? එහෙම වෙන්න පුළුවන්ද? දැන් list එකකුත් තියෙනවා. list එකක් දිගයි. Do you believe this or not? Yes, no, maybe, not sure. But you have the proof. Then how are you going to explain this? Sorry. විශ්වාස කරන්නේ නැහැ කියමුකෝ දැන් මේ ලිස්ට් එක දැක්කම කොහොමද කියන්නේ? එහෙම නම් වෙන්නේ නැහැ කියලා. So we'll do a fun experiment. We'll do a fun experiment and see how it's going to work. Now, believe you have an astrologer. Payne කෙනෙක් කෙනෙක්. Payne හරි හඳහන් බලන හරි astrologer කෙනෙක්. So I haven't done any studies on astrology side in statistically as well. This is just an example. Okay, මම ওই පැත්ත statistically analyze කරලා නැහැ. ඒකෙන් ඒක නම හරියටම ඔව්ද නැද්ද බෑද කියන දන්නේ නැහැ. නමුත් මේ example එකට මම එහෙම එකක් පාවිච්චි කරනවා. Right? So the idea is now she claims she can improve the luck of the people. She said she can improve the luck of people. She can make unlucky people lucky. And she's going to prove it scientifically. She's going to do an experiment and scientifically going to prove she can actually improve the luck of people. Tough claim. So let's say how we can do it. So she get 100 people as sample for this test. And how are you going to measure the luck? Okay, this is the way she's going to measure the luck. So she has a pot, like a jackpot, and in it he has 500 rupee bills and 5 blank pieces of paper. Right? In this box or pot, 5 blank papers and 500 rupee papers, rupee notes, currency notes. Now she asked each one to come and pick 5 items from this box without looking. Randomly pick 5 items. And if the person picks, let's say 200 rupee notes and 5 blank papers, she will give 200 rupees to that person. Or he can take whatever he had picked. Now remember, now every time a new person comes, she fill it back with all the 5 currency notes and 5 blank sheets. Otherwise, after the first 10 people, the box will be empty. So it's not like that. After each person comes and pick 5 items, she refill the box back to the original way. Right? Now, there are different ways people can get output. Some might get only 5 papers, some might get 5 notes, some might get 3 notes, 2 papers, like that. So what do you think the luckiest person is going to get? How much money is the luckiest person can get? $500. Good. Do you think everyone can get 500 rupees? What is the lowest amount a person can get? 0, right? So the way she's going to measure the luck is by the amount of currency they have won, amount of money they had won, right? That kind of makes sense, right? If you're lucky, you get 500 rupees. If you are really unlucky, you don't get anything. If you're somewhere in the middle, you get 200, 300 or whatever, like sweepstakes. Right. So let's see whether we can actually do this one. Right, let's do it online in a different way. So that might be interesting. Now you have 5 different coins, right? Sorry, 10 different items. I want everyone to select a number from 1 to 10. You don't have to put it in the chat. Just write 5 items, 5 numbers between 1 and 10. So it's like simulating the picking of different items. You can include 1 and 10 in your numbers. Right? Liver then ඕගොල්ලෝ 1යි 10 අතර 1යි 10ට ඇතුළුව සංඛ්‍යා වලින් ඉලක්කම් පහක් තෝරගන්න. තෝරගෙන කොහේ හරි කොලයක හරි කොහේ හරි ලියන්න. You have the lunch in the next session, right? So you can just take extra 2 or 3 minutes and we'll finish this one. You are the කොලයක හරි notepad එකේ හරි කොහේ හරි ලියාගත්තද? Done? Now I am going to be the astrologer, so I am going to put 5 numbers I think as the lucky numbers. Those who have these numbers will get 100 rupee. Okay, not in the real life, okay? In this example only, 100 rupee for each match. දැන් අපිට ඇත්තටම box එකක් නැහැ නේ. ඒකින්ද මම මේ ඔයගොල්ලෝ numbers පහක් ලියන්නේකෝ මම numbers පහක් දානවා. ඒ පහයි ඔයගොල්ලන්ගේ පහයි match වුණොත් ඒ match වෙන හැම number එකටම ඔයගොල්ලෝ මේ රුපියල් 100ක් ඇදුණා කියලා හිතා ගන්න, right? Here trip ticket එකේ තමයි. So any number that you match, you get 100 rupees. Finished? ලියලා ඉවරද ඉලක්කම් ටික?
Also,
Okay. Here's the lucky numbers.
Okay.
Now compare it. 2, 3, 8, 5, 1. Compare it and calculate how much money you have won. Can you put the amount you won in the chat just for the fun? 2, 3, 8, 5, 1. Oh, RC chat. Good, good. Now we have 94 people. How many of you have won? Now I want to get the least lucky people. Right? So my claim is I can make you lucky. My claim එකේ තියෙන්නේ ඔයගොල්ලෝ මේ වාසනාව වැඩි කරන්න පුළුවන් කියලානේ. කීයක්වත් ඇදිච්ච නැති හරිය නැත්නම් රුපියල් 100ක් ඇදිච්ච කී දෙනෙක් ඉන්නවද? How many of you have won 100 rupee or less? එහෙමයි ඉන්නවනම් yes කියලා දාන්න. ඇත්තටම දෙන්නේ නැහැ හොඳේ. 100ක් හෝ ඊට අඩුවෙන් ඇදිච්ච අය ඉන්නවද? Okay, 1. Only 1, 2, 3, 4. I don't know rough estimate about how many people are really unlucky in my class. Anyone with 0 money? බින්දුවටම බහපු කවුරුවත් ඉන්නවද? හැමෝටම 100ක් හරි ඇතිනවද? ඔව්. Okay, right. Now, next instructions are for the people who have 100 or less cash. Right? Now, you are the unlucky people because others got 200, 300, 400. I don't know whether you have 500, but they all want a lot of money than you. They are lucky people. You are the unlucky people. So now, I am going to do a magic on you, a charm on you. දැන් ඔය 100 හෝ ඊට අඩුවෙන් ගත්තු අපේ අවසනාවත ළමයි ටික ඉන්නනේ ඔයගොල්ලෝ තමයි මැජික් එකක් කරනවා. After we did the magic charm, your luck will increase. ඔන්න ඔක උනාට පස්සේ ඔයගොල්ලන්ගේ වාසනාව වැඩි වෙනවා, right? Now this is only for the people who have 100 or less. I want you to write again, repeat the previous scenario, repeat again, write 5 numbers. දැන් ඔන්න අර 100ට අඩුවෙන් ගත්තු අවසනාවත ළමයිට මැජික් එකක් කළා. දැන් දෙවෙනි පාර මම chance එක බලන්න හදන්නේ. ලක් එක අඩු වුණාද වැඩි වුණාද කියලා. ආයි පාරක් ඔන්න දැන් ඔයගලන්ට මැජික් බෝඩ් මේ පොට් එක දෙන්න හදන්නේ. ඉලක්කම් 5ක් ලියන්න. අර 100ට හෝ ඊට අඩුවෙන් ගත්තු කට්ටිය විතරයි හරිද? ඉලක්කම් පහක් ලිව්වා නේද? Yes, no, done? Right. Here are the lucky numbers for the second round. On the දෙවෙනි පාර lucky numbers ටික දානවා. 4 6 1 8 9. මේ පාර 100ට වඩා හම්බ වෙච්ච කට්ටිය කී දෙනෙක් ඉන්නවද? මට කලින් පාර 100ට වඩා අඩුවෙන් හම්බ වෙච්ච කට්ටිය හොයාගන්න බැරි. නමුත් මම හිතන්නේ 1 2 3 1 2 3යි 4යි 5යි. පහක් හරි හයක් හරි ඉන්නවා. I think there are only 6 people. Now from 6 people, how many of you have got more money this time? කලින් පාර 100 හෝ අඩුවට හම්බ වෙච්ච අයගේ දැන් ඊට වඩා වැඩි හම්බ කී දෙනෙක් ඉන්නවද? 6ක් හිටිය ඕන දැන් කට්ටියට ලක් එක වැඩි වෙලා තියෙනවා. 1 2 3 4 5යි 6යි. හරි කලින් 6 දෙනෙක් හිටියා. 6 දෙනාටම 100ට අඩුවෙන් හම්බුනේ. මම මැජික් එකක් කළා. මැජික් එක කළාට පස්සේ මොකද උනේ? ඔන්න 400 දිනපු අය 300 දිනපු අය නා 300 දෙන්නෙක් 3 දෙනෙක් ඉන්නේ. මැජික් එක වැඩ කළා නේද? Didn't the magic work? Earlier you didn't get money. You had only 100 or less than that. But now everyone who's in the unlucky groups get more money. You have become more lucky. නේද? කලින් බොහොම අවාසනාවන්ත ළමයි ටික තෝරලා මම මැජික් එක කළාට පස්සේ හැමෝටම දැන් රුපියල් 400 300 හැදෙනවා. ඒ කියන්නේ මැජික් එක හරි. charm එක වැඩ. Right? So do you believe that it's because of my magic charm? එහෙනම් වෙන්නේ magic charm එක කියලා හිතපු කී දෙනෙක් ඉන්නවා? එහෙනම් කොහොමද උනේ? But again, the charm works fine. So this is the case. If you look at a random distribution, we'll talk about probability later. Good, some people already know about probability. If you should have a distribution like this, just think about the height of the students in your class. Most of them are average height. There can be few very tall people and few very short people. Most of them are in average height. Similarly, when you randomly pick 5 items, most of you will get an average value like 300 or something like that. Very few will get 500, very few will get 0 or 100. That is because of the probability. So next time when you select this group and repeat it, again, most of them will get average to around 200 or 300. Then make the average 200 or 300. So if you selected this person, this group, and compare it again, you will think, okay, earlier it was 100, but now it has gone to 300. But in reality, what's happening is you are basically moving towards the mean. If you have selected the very lucky people and repeated them, I don't think they will be lucky again. If you are lucky at 500 rupees, next time you will not likely to win another 500. Most likely you will get around 200, 300 something. Similarly, if you got only 100 rupees, next time probably you will get 200 or 300. That is the most likely value. So this is called the regression towards the mean. So this is what's happening in here as well. Now sports, there is a good amount of effect from the skill and practices, but there is also a little bit of luck and probability and everything. Right? So if now who comes at the front page or the cover, සාමාන්‍ය magazine එකේ cover page එකේ කාවත් දාන්නේ පැරදිච්ච group එකක් දානවද? ගන්නම දෙයක් නැති group එකක් cover page එකේ දානවද? What do you think? In the sports magazine, what kind of people do you expect to come in the cover page? People who won a championship or the people who lose? Usually people who win it, right? Who won the championship, who have won many matches. Those will be the people coming to the front page. But to win a championship, there is a certain amount of randomness and probability associated with it. If everything fits into the place, it's very easy for you to win the championship, right? Your group work perform quite well, the weather is good and everything fits into together and team works with as a team and everything happens, then you get to the highest win rate and you show it in the cover page. But you can't always have the same luck or the same probability. Then in the following year, most likely, you will not be able to show the same performance. Right? You will not likely to pay the same performance. Then what's going to happen is, next year you will be performing poorly than this one, right? So this is one of the pitfalls that I mentioned. This actually happens much more common than you think. For example, I remember in a particular country, they started a new training program for the fighter pilots. And they said this particular program is making the pilots more accurate and make them more, let's say, fast and accurate. But how did they do it? What they have done is, in the pilots group, you have a pool of pilots. They have selected a group pilots who are performing quite bad and put them into this training program. They said, okay, these pilots are not well performing, so let's train them further. Right? So we'll put them through this new training program. After the training program, the performance was good. But when they did a statistical analysis, they found the program actually did nothing. What had happened was, sometimes due to randomness and randomness, your performance can go down. So that particular month or week, the performance are very bad of that particular group, particular set of pilots. And whether they've gone through the training or not, next time they are most likely to perform better. Because of performing better has nothing to do with this magic or charm or anything, just randomness. Right? Just think about your everyday life as well, right? Sometimes you have a very bad time in your life and you go to some horoscope or do something and suddenly everything seems to be turning good. Now, since I haven't done any scientific survey on horoscope or anything, I don't know whether it really has an effect or not. But keep in mind, this might also be a reason that you might feel like it. What randomness, probability, in mind that regression center, regression to means might play a role. This doesn't apply for everything, but for things that has randomness, probability, and things like that, keep this in and keep an open mind, and you will start to notice many places where this thing is playing and people interpreting it as a different thing. Maybe superstitious, maybe something else, I don't know. Right. So I have taken extra 10 minutes from your time, but I hope you learned something from this last one. So this one is not about exams or coming for the paper or anything. This is just, as I mentioned, giving you some common sense and how to apply science, maths, and stat into your life. Right. Now, with that, I will conclude today's lecture. Any questions you want to ask, either from the earlier one or from this presentation, the new one? No question. Then we'll wind up for today, and I wish you all the best for the next hour. And
Recording
can
stopped.